This video is for finding intervals of concavity and points of inflection for trig functions. Before we do that, we're going to do a quick review of intervals of increase and decrease and relative extrema for those trig functions. So again, what I like to do is take that function, plug it in the calculator. This one has a domain restriction. So we're going to hit window, put in 0, and then 2 pi. So 2 second pi. And then to graph it, you're going to hit zoom fit, which is 0. And so we get a graph like this. So we can see that we're going to be getting a max here and a max here. So critical numbers at 0 and 2 pi. And then it's decreasing to here, and that's our min. So we should get a critical number right in the middle, which is pi, right? And then it's going to increase. So we should get decrease, pi, increase. But we still got to do this all analytically. So first thing, let's take our derivative. So f prime of x equals -2 sine x. And then this is chain rule. This is cosine of x squared. And so it would be plus 2 cosine of x times the derivative of the inside, which is negative sine x. So we end up with f prime of x equals -2 sine x minus 2 sine x times cosine x. And so you can see we have a common factor, so we factor that out. And we end up with 1 plus cosine x. And then again, any derivative, we set it equal to 0. So we would get sine x equals 0, and 1 plus cosine x equals 0. So cosine x equals -1. So on our interval from 0 to 2 pi, we know that x is equal to 0 and 2 pi for sine. And this one would be x equals pi, which are the three that we got. So we're going to put 0 here, 2 pi here, pi in the middle, and then cross these off because they're outside of our domain. So now we just need to plug in our derivative. So we're going to try something in between. So how about pi over 2? It's a nice number. And then over here, we'll do 3 pi over 2 to find our value. And again, we're going to plug it in here to determine if it's positive or negative. Now, looking at the graph, we already know it's negative on the left and positive on the right because it's increasing. So we could just cheat right now and say negative decrease, positive increase. But we should still do this analytically. So if we plug it in, we already have a negative and then pi over 2. And so we're just looking for positives and negatives, and we got our unit circle here. So at pi over 2, right, our sine function would be 1 and our cosine function would be 0. So it would be positive, positive, and positive. So negative, positive, positive. So negative times a positive times a positive is a negative. It checks. And then 3 pi over 2, so now we're over here, right? And so it's negative. Our sine is negative, so that would be negative times a negative. And then again, our cosine is 0, so positive. There's our positive. So everything's checking perfectly. So we have our interval of increase. So it's increasing on the interval from pi to 2 pi. And we'll put a parenthesis there because it is a point, a critical number. And then it is decreasing from 0 to pi. And so we would have a relative min at pi. So a relative min of what? Let's plug pi in and see what we get. So trace second pi, hit enter, and it says -1 at pi. So yeah, we do have these as endpoints here, and so we're not supposed to include them as relative extrema, but you could, even if you wanted to, say that we would also have a relative max and a relative max at 0 and 2 pi. I wouldn't complain about that. But it's technically an open interval, so we won't include the 0 and the 2 pi. All right. So we're going to now follow those exact same steps, but with the second derivative. And so for the first, it gives us increase and decrease and relative max and min. And with the second derivative, it'll give us, this would be concave down and concave up. And these would be points of inflection. So Let's take the second derivative and see what we get. So let's rewrite our first derivative, which is right here, negative 2 sine x. So f prime of x equals negative 2 sine x minus 2 sine x cosine x. And yeah, you could use either one. You could use product rule on this or use a normal derivative product rule, but we're going to stick with what we have here. Okay, so f double prime of x equals, and then this would become negative 2 cosine of x minus, and then it's product rule. So minus 2 sine x, and then I'll just get rid of that minus. We'll take care of it later. And cosine x. So derivative would be minus 2 cosine x. And over here we would get minus sine x. And then we do our little cross multiply. So it will be minus 2 cosine x, so minus 2 cosine squared x. And then plus 2 sine squared x. And so we'll set this equal to 0. And hopefully you'll see that they all have 2's. So right off the bat, we can just divide everything by 2, giving us negative cosine x minus cosine squared x plus sine squared x. And then if you remember solving these, we like to make them all the same trig ratio. So we're going to turn our sine squared into cosine using our Pythagorean identity. So this would be 1 minus cosine squared x. And so now we have negative cosine x minus 2 cosine squared x plus 1 equals 0. And so that is a quadratic. So I'm going to take it over here to finish it, putting them in order. So this would be negative 2 cosine squared x minus cosine x plus 1 equals 0. Dividing everything by negative to make the leading term positive. And then we factor. So this would be 2 cosine x cosine x. You just think of them as your x's, your a's and b's. Okay, and so now we need the middle one to be positive, so we'll put the minus 1 here and the positive 1 here. And then if we check it, we get 2 cosine squared x, 2 cosine x minus cosine x, which would be cosine x, and then negative 1 and negative 1 is positive. All right, so now we have 2 cosine x equals 1, and cosine x equals negative 1. So cosine x equals a half, and cosine x equals negative 1. So we go back to our unit circle and check and see what that is. So we're only looking between 0 and 2 pi. So when does the x-coordinate equal to half? It's at pi over 3. And then it's also going to be at 5 pi over 3. So pi over 3, 5 pi over 3. Those are our x's. And then also cosine x equals negative 1. So that's our x-coordinate, which is at pi. So we put those on the graph. So we have pi over 3, pi, and 5 pi over 3. Now what I'm going to do is also put on there 2 pi, because we needed to make sure that we stop our interval. And on the other side, 0. All right, so now we have 3 intervals. And if you check your calculator, you can see it's concave down, and then concave up, and then concave up, and then concave down. So the middle one's a full concave up, but it's picking pi as a stopping point, which it's not. So it'll be concave down to pi over 3, concave up from pi over 3 to 5 pi over 3, and then concave down. So we should be getting concave down, negative, concave down, negative, concave up, positive, and concave up, positive. So now let's just check with our second derivative. So we're going to plug in something between 0 and pi over 3. And if you don't know what that is, you can just use the unit circle. So pi over 6 or pi over 4 will work. I like pi over 4, so I'm going to use that. And then something between pi over 3 and pi. So between pi over 3 and pi, how about pi over 2? And then the same thing, if we're going to go from pi to 5 pi over 3, why not 3 pi over 2? And then the final one is 5 pi over 3 to 2 pi. So somewhere in here, how about 7 pi over 4? because I love those 45s. So f prime, double prime of 7 pi over 4 equals. And so we're going to be getting a negative, a positive, and a negative. So if we look at our function here, we've got to use this one, not the one that we've changed and modified. So that actual second derivative right there. So this would be rad 2 over 2, right? And this would be rad 2 over 2 squared. And this would be rad 2. So these two are going to cancel. So it's only this one that we have to worry about. So it's negative. Check. And then the second derivative of pi over 2, same thing. Cosine is going to be 0. So those are zeros. And so all we have to deal with is that one, which is 1. So that's positive. And then 3 pi over 2 is down at the bottom here. See, it's right here. So our cosine would be 0, and our sine would be negative 1. So it'd be 0, 0, negative. But again, squaring it makes it positive. And then the 7 pi over 4 right there is at the square root of 2 and negative square root of 2. So again, when you plug them in here, they cancel. So we only have to worry about this one. And cosine is positive in quadrant 4. So that would come out to be negative again. And there you have it. Everything is perfect. So we are increasing, or sorry, I'm already on this first derivative. Concave up from pi over 3 to pi over 3. 5 pi over 3, sorry about that. And then concave down, let's put that in red. From 0 to pi over 3, union 5 pi over 3 to 2 pi. And do we have points of inflection? I'm writing points of inflection, so of course we do. Wherever there is a change in concavity, that is a point of inflection on these continuous functions. So we have a change in concavity here at pi over 3. And we also have one at 5 pi over 3. So we just need those values. And we want to plug them in anyway just to verify that is that point of inflection. If we get something up here, you can see it's part of the concavity. That's not good. So trace second pi divided by 3. Hit enter, and it says, see how it's perfect. That's a concave down, concave up. So 1.25. And I guarantee the other one's the same because it's symmetric. So trace 5 second, hold on, 5 second pi divided by 3, 1.25, perfect. So that's a point of inflection because the concavity changes. That's a point of inflection, concavity changes. So with the trig functions, you're going to have to get a little creative and algebraic and go back to your pre-calc stuff and trig to solve these. But it's the same exact rules as we would have used for a polynomial.